Good morning and welcome to PsyQuil. I'm your host, Wraith, and this is another edition of PsyQuil Daily News. Today we're going to be looking at quantum mechanics, in particular the quantum processor and a new particle that has been discovered. This article is from phys.org, written by Anne Manning on February 21st. A new phase of matter, physicists achieve first demonstration of non-Abelian anyons in a quantum processor. A new phase of matter. Physicists achieve first demonstration of non-Abelian anyons in a quantum processor. Our physical 3D world consists of just two types of particles: bosons, which include light and the famous Higgs boson, and fermions, the protons, neutrons, and electrons that comprise all the stuff, present company included. Theoretical physicists like Ashvin Vishwanath, Harvard's George Bessemer Leverett Professor of Physics, don't like to limit themselves to just our world, though. In a 2D setting, for instance, all kinds of new particles and states of matter would become possible. Vishwanath's team used a powerful machine called a quantum processor to make for the first time a brand new phase of matter called Non-Abelian topological order. Previously recognized in theory only, the team demonstrated synthesis and control of exotic particles called Non-Abelion Anyons, which are neither bosons nor fermions, but something in between. I'm going to pause there and do a quick review of particles. So this is called the standard physics model, the standard particle model. Here we have the boson section in red and yellow. These are all the bosons, okay? And here in the purple and then below in the green, we have the fermions. They are categorized based on their spin. So bosons have a 1 spin. They have what's called a full 1 integral spin. And so this counts as a 1 integral as well. It's not a half. And then these fermions have a half spin. I'm not going to go into detail on spin. Suffice it to say that it has to do with quantum mechanics and shows up quite often in electromagnetism. I do want to add one other little quirky point here about protons and neutrons. Here we have what are called quarks. This whole section is quarks. And these two are the up and the down quark. A proton is made up of 2 up quarks and 1 down quark. And a neutron is made of 2 down quarks and 1 up quark. Now right here you see the charge, 2/3 and -1/3 for the down. So if you were to sum that up, 2/3 plus 2/3 plus -1/3, you'll end up with a +1 charge. And that is how you get the proton. And then of course, if you do the same for the neutron, you sum 2 downs plus 1 up, you get -1/3 plus -1/3 plus 2/3, you get 0 charge. And that's how you get your neutron. Just a little informational piece for you there. Now, let's get back to our article. Their results are published in Nature in collaboration with researchers at the quantum computing company Quantinuum. So just so you know, this is the article, in case you're interested in reading that further. Non-Abelian topological order and anyons on a trapped ion processor. Non-Abelian anyons, known to physicists as quasi-particles, are only mathematically possible in a 2D plane. The qualifier quasi refers to the fact that they are not exactly particles, but rather long-lived excitations through a specific phase of matter, say think of ocean waves, and they have special memory carrying capabilities. Besides the fact that creating a new phase of matter is exciting fundamental physics, non-Abelian anyons have been widely recognized as a potential platform for quantum computing, which infuses the research achievement with even more significance. Non-Abelian anyons are inherently stable. This is really key. Remember this point. Unlike the flimsy and error-prone quantum bits or qubits on other quantum computing platforms, they can remember their past as they move around one another like a magician shuffling cups with hidden balls. This property is also what makes them topological, or able to be bent and twisted without losing their core identity. For all these reasons, non-Abelian anyons might someday make ideal qubits, units of computational power that extend well beyond the classical computers of today, if they can be created and controlled at larger scales. That's enough for the article. I could go into more there, but it's not that important. What I want to do is discuss the actual qubit a little bit. So remember this point about the non-Abelian anyon being inherently stable, because qubits are actually very much not stable, and this is one of the problems they're having in quantum computing. So what is a qubit? Well, let's talk about that. A qubit, short for quantum bit, is the basic unit of information in quantum computing and counterpart to the bit, binary digit, in classical computing. A qubit plays a similar role as a bit in terms of storing information, but it behaves much differently because of the quantum properties on which it's based. And I should point out at this time 2 things. One, that the qubit is actually a particle, In a quantum computer, a number of elemental particles, such as electrons or photons, can be used. In practice, success has also been achieved with ions, with either their charge or polarization acting as a representation of 0 and or 1. Each of these particles is known as the qubit. The nature and behavior of these particles, as expressed in quantum theory, form the basis of quantum computing. Two of the most relevant aspects of quantum physics are the principles of superposition and entanglement. Qubit and superposition. So superposition is a really important part of the qubit and quantum mechanics period. This is what really gives quantum computing its power. When used as a qubit, a particle is placed in a controlled environment that protects it from outside influences. For example, it might be floated in a magnetic field or embedded in specialized circuitry, but is then isolated from the outer environment. In many cases, the entire mechanism is encased in a refrigerated compartment to minimize subatomic disturbances, with temperatures often near absolute zero. So in order to ensure that they have some level of control over the environment, which is needed because they are very unstable, they have to make it near absolute zero, or they use some sort of magnetic field. Researchers are now experimenting with a variety of approaches to creating an environment in which the qubits can be reliably manipulated and measured without being affected by outside factors. For example, one approach is to suspend an electron in an electromagnetic field and control the electron's spin state, while isolating the electron from external influences. When the electron's spin is aligned with the field, it is in a spin-up state. When it is opposite to the electromagnetic field, it is in a spin-down state. So, same direction, up, opposite direction, down. The electron's spin can be changed from one state to another by directing a pulse of energy at the particle. The energy might come from a laser beam, microwave, or another source. Each time the pulse is delivered, the electron's spin state changes. So it's just like an on-off switch. So far, it's just like a regular bit. The switch in state provides a mechanism for assigning a 0 or a 1 to each qubit, similar to a bit in classical computing. However, quantum computing makes it possible to do much more with a qubit. Suppose that the energy pulse delivered to the electron is 1 unit of energy. What happens then if the pulse is only 1/2 a unit of energy? According to quantum law, the particle enters a state of superposition, behaving as if it were in both the spin-up and spin-down states simultaneously. It's sort of like the slit experiment. They don't know which state it's in now. They've done a half a pulse. It could be in the 1 state or the 0 state. It could be either. The electron exists in a fluid state of probability that is mathematically represented by fractions between 0 and 1. It remains in this state until it is observed and measured. The superposition property enables a quantum computer to be in multiple states at once. The number of possible states grows exponentially as the number of qubits increases. The possible states are represented as 2n, where n is the number of qubits. 2n is also our calculation for binary numbers. The following table shows the number of possible states for 5 qubit amounts. So this just looks like binary math. You've all seen this if you've done computer science 100 times. However, the key point here is about to be shown up. A quantum computer can do much more with its qubits than a classical computer can with the same number of bits. This is the key part. For example, a 2-bit register in a classical computer can store only one of 4 binary configurations, 00, 01, 10, or 11, at any given time. However, a 2-qubit register in a quantum computer can store all 4 numbers simultaneously. This is the difference. To achieve this type of growth, however, quantum computers must also take advantage of another important quantum property, entanglement. Right, so because of the fact that there's probability, we won't actually know which numbers are stored in there, right? It could be a 0, it could be a 1, it's not known. This is where entanglement comes in. When particles are generated or interact in certain ways, they become entangled. That is, they retain a connection with each other even if separated by long distances. As part of this connection, their behavior is correlated across these distances as long as they remain entangled. Quantum computing uses this correlation to achieve the type of exponential growth promised by the superposition state. So, entanglement is a really wild concept. I urge you all to read on it. But for the purposes of this understanding, all you need to know is that 2 particles can be what is called entangled. And if you know one of them, then you know the other. You know the state of the other. It doesn't matter what the distance is between them. And by that I mean really large distances. Like the particles could be separated by the distance from the Earth to the Sun, and they would still have that same interaction. So it's pretty wild stuff. Anyway, they use this entanglement to then be able to determine those states that were undeterminable before. Now, that's as far as I want to go with entanglement because I don't fully understand it. Physicists don't really understand it. They know that it works, they accept that it works, and they know how to work with it, but they don't know the how of it. Anyhow, that's basically the article. I wanted to go over what qubits were. I hope you understand that. I wanted you to get a taste of what qubits are and how quantum computing works. But the key takeaway from this is that these researchers have found this non-Abelian anyon that only works at the second dimension. Okay, they've managed to make it like a, what would you call it, a quasi-particle, all right? Because it won't perform like a fermion or a boson, which performs in the 3D world. Essentially, though, the non-Abelian anyon will allow them to have a stable environment with which to do quantum computing. They're hoping that they will be able to use these particles as the qubits and that they will be stable, and so they can produce a solid quantum computer with it. That is the key takeaway. Anyhow, one last thing I want to show you. If you're interested in particles at all, I found this cool little site, particleadventure.org, index.html is your URL. I will be posting it in my description below. Here you can go over at your own pace into any of the particle physics stuff that's well known. All kinds of questions in here on things. You can follow at your own pace, and it will teach you all the fun fundamentals of particles and how they work. And I urge you all to do it. Don't be afraid. I mean, it's physics. It's super fun. It's complicated, yes, but this stuff is distributed in a way that should be relatively easy to understand. Anyhow, let me know what you all think about quantum computing. What do you think about this anyon technology that they have come out with? And please like and subscribe, and I'll see you in the next video.